Hi everybody, this lesson 3.3 is an extension of our previous lesson where we talked about the Maclaurin series. The difference here is we're going to talk about a different series known as the Taylor series. So they're very similar in that you remember the Maclaurin series, we use the derivatives of a certain function f at x to try and make an approximation of it. Okay, so the Maclaurin series was an infinite series, and so it had an infinite number of terms, all with an increasing value for x. Okay, so x squared, x cubed. And their coefficients were found by taking first the function and substituting in x equals 0, then the first derivative, second derivative, third derivative, and it keeps going to infinity. Now we only usually calculate, the first 3, 4, 5, 6 terms. And for values of x that are small, the Maclaurin series can provide reasonable approximations. The Taylor series, on the other hand, can provide much more accurate estimations at different x values. The only difference is instead of substituting in x equals 0, we're substituting in some value a. Okay, and I'm going to show you both ways. The first where I provide you with what the value of a is, and the second set of examples where we use the data we have to pick an appropriate value for a. So the way this function changes is, remember, from the Maclaurin series, we substituted in 0 to solve for the coefficients. In this case, two items happen. The first is we substitute in a for each of these coefficients. They're still exactly the same. The function at a, the first derivative, second derivative, third derivative. The second item is our x now becomes x minus a. Okay, so x minus a squared, x minus a cubed. These formulas will be provided to you, okay, so you don't have to worry about memorizing them. But the difference is that this series here is known as the Taylor series. So when we say it's a, we mean it's centered around some function or some value a. If you were to actually graph the series, if you graph it using the Maclaurin values, which are when x is 0, and the Taylor series where x is a, you will see that the entire graph shifts to that point a. Okay, so the approximations are similar. It's just that it takes less terms with the Taylor series to develop a good estimation. So we're going to jump right into examples. So I've shown you what the Taylor series is. We've learned kind of how to derive that overall series when we talked about the Maclaurin series. So now I'm going to show you a couple of examples. Find the first 4 terms of the Taylor series expansion of f at x equals 4 divided by x plus 6 at a equals 2. So I start these questions by writing out the starting point of the Taylor series expansion. So we have f of x is equal to f at a plus f prime at a times x minus a plus f double prime at a over 2 factorial x minus a squared. And our last term, f, the third derivative, f at a over 3 factorial times x minus a cubed. And this would continue on, but we're only calculating the first 4 terms. So we know that f of x is equal to 4 over x plus 6. You can also write that as 4 times x plus 6 to the negative 1. So our first derivative, f prime of x, is equal to 4 times negative 1 times x plus 6 to the negative 2. Okay, so that's using the power rule. Keeping in mind that the derivative inside this function of x plus 6 would simply be 1. So I'll show it here, but I will omit it for the next 2 derivatives. So simplifying that, we get negative 4 times x plus 6 to the negative 2. The second derivative is equal to negative 4 times negative 2, x plus 6 to the now negative 3. Simplifying that, we get 8 times x plus 6 to the negative 3. Our final derivative, the third derivative, is equal to 8 times negative 3 times x plus 6 to the negative 4. Okay, again, just using the power rule each time. So we arrive at negative 24 times x plus 6 to the negative 4. So now that we've found all of our derivatives, in order to substitute them in for the coefficients, we have to evaluate them at a. So our first one, okay, we have f of a, and that's equal to 4 divided by 2 plus 6, which is 4 divided by 8, which is equal to 1/2. The first derivative, f prime of a, is equal to negative 4 divided by 2 plus 6 squared, which is negative 4 over 64, or in this case, 1 over 16. Okay, sorry, negative 1 over 16. So I'm just, in case you're wondering, I show them with a negative exponent. I've just moved them into the denominator here. Having them in the numerator makes it easier to do the derivatives, but when we're solving for values, it's easier to have positive exponents, which is why I moved it to the denominator. For the second derivative, f double prime at a, it's equal to 8 divided by 2 plus 6 cubed, which is equal to 8 divided by 512. And if you simplify that to keeping it as a fraction, you would get 1 divided by 64. Oftentimes, you can put that number in your calculator, and there's a button that usually either looks like a fraction that says something like d divided by c, or sometimes it looks like a big one, like capital A with a b over c. Sorry, b over c. So when you get your final answer, you can press one of those buttons. It looks different on each calculator, and it will convert it to a fraction. Okay, so if you write something like 8 divided by 512, and you press the button, on my calculator anyways, it shows up with a 1, and then it shows a symbol like this, and 64. So that means 1 over 64. Okay, so don't think that you have to show each of these and reduce them yourself. Most of the time you will be able to do this completely using your calculator. Okay. Our last one, our third derivative, f triple prime at a, is equal to negative 24 divided by 2 plus 6 to the exponent 4. And if you calculate that last one out, you get negative 3 divided by 512. Again, using your calculator. Okay, in your first step here, you would get negative 24 divided by 4096. If you place it in your calculator using the fraction button, okay, you'll end up with negative 3 divided by 512. So now we can substitute each of those values in. Okay, so our function f at x becomes f at a, which is 1/2, plus f prime of a, which is negative 1 over 16 times x minus a, which is 2, plus our third term, okay, f double prime of a, which is 1 over 64 times x minus 2 squared, and that's, remember, divided by 2 factorial, plus our last term, okay, in this case I had a plus, but it's actually a negative, so minus 3 over 512 times x minus a cubed divided by 3 factorial. So you can simplify these last couple terms. I'll add the pluses at the end. And you end up with f of x is 1/2 minus 1 over 16 times x minus 2 plus 1 over 128 x minus 2 squared minus 1 over 1024, again using my calculator, x minus 2 cubed. And you can see that in these examples, as the denominators increase, those numbers are going to become increasingly smaller. So after you've done, even the third term, okay, 1 divided by 128, that's 0.007812. Like, we're getting into really small numbers. By the time you get into 1 divided by 1024, okay, you're getting into, all the way down to 4 decimal places, 0.0009765, and it keeps going. So you're getting a very small number. So what this means is that the Taylor series converges upon a solution very quickly. The further you go on with terms, the higher this denominator becomes, right? And that means that it's a smaller and smaller and smaller number that add to it. And we'll see in future examples in this lesson why that's important. Okay, so when I ask you to find the first 4 terms, this would be the solution that you would come up with. Okay, so our second example, find the first 4 terms of the Taylor series expansion of f of x equals 3 times the square root of 2x at a equals 2. So again, I start this by writing out the first 4 terms of a Taylor expansion. So we have f of x is equal to f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus our last term, the third derivative, f triple prime of a over 3 factorial times x minus a cubed. Okay, and that would obviously continue on, but we're only finding the first 4 terms. So then again, I'm going to start by writing the function. So I have f of x is equal to 3 times, I will write it in terms of an exponent because then we can just use power rule to solve for it. 3 times 2x to the exponent 1/2. Okay? So our first derivative, f prime of x, is equal to 3 times 1/2 times 2x, in this case to the negative 1/2, subtracting 1. Then remember, you have to take the derivative of the function inside. So the derivative of 2x is 2. So you multiply it here by 2. If you multiply all of those out, you get f prime of x is equal to 3 times 2x to negative 1/2, because the 2 in the numerator and the denominator will cancel. The second derivative, f double prime of x, is equal to 3 times negative 1/2 times 2x. In this case, we're at the negative 3 over 2, subtracting again 1 from the exponent, and again multiplied by 2 for the derivative of the function inside. If we do that again, the 2's here will cancel, and what we end up with is negative 3 this time times 2x to the negative 3 over 2. Okay, so that's f double prime of x. The third derivative, f triple prime of x, is equal to negative 3 times, in this case, negative 3 over 2, the exponent, times 2x, and then subtracting 1 again from the exponent, we get negative 5 over 2. And again, we're multiplying by the derivative of 2x, which is 2. So simplifying this, these two 2's will cancel, and we're left with positive 9, because it's negative 3 times negative 3, times 2x to the negative 5 over 2. Okay, so we have our functions here. Now we're going to substitute in our value of a, which is 2. So we have first f at a, okay, which is equal to 3 times the square root of 2 times 2, which is 3 times the square root of 4, which in this case equals 6. Our first derivative, f prime at a, is equal to 3 times 2 times 2, in this case to the exponent negative 1/2. You could have also written it as 3 divided by the square root of 2x. Either way works. If you multiply that one out, you get 3 divided by 2. Okay. Again, you can use your calculator with exponents to calculate these. And then use, again, remember that button, A. Mine looks like this, a big A with a B over C beside it to convert them to fractions. Okay. You can leave them as decimals, but I find when you get to your final answer, it's easier to write them all as fractions. Our second derivative, f double prime at A, in this case, is equal to negative 3 times 2 times 2 to the negative 3 over 2, which in this one comes out to 9 divided by 32. Okay, again, using your calculator. Okay, sorry, not 9 over 32, that's for the next one. It's negative 3 over 8. My bad. I'm looking at my sheet where I have the little numbers out, and I looked at the wrong one. Our third derivative, f triple prime of a, is equal to 9 times 2 times 2, in this case to the negative 5 over 2. And in this one, it comes out to 9 over 32. So again, sorry, I used the wrong number there. So now we can substitute each of these values in. So we have f of x is equal to our first function, f at a, which is 6, plus f prime of a, which is 3 over 2, times x minus a, which is x minus 2, plus our next term, which is negative 3 over 8, divided by 2 factorial, remember, x minus 2 squared, and our last term, which is plus 9 over 32 divided by 3 factorial times x minus 2 cubed. Okay, and obviously that would continue on if we did more terms. Simplifying each of these, we get our final function is equal to 6 plus 3 over 2 x minus 2 minus 3 over 16 x minus 2 squared plus 3 over 64 x minus 2 cubed. Again, using your calculator to solve those, or if you want to, you can write them as decimals. Okay, so when I ask you to find, again, the first 4 terms, that would be the kind of final answer I'm expecting. So we're not solving it and coming out to a number in these types of examples necessarily. So in addition to expanding out functions as a series expansion, you can also estimate the values of functions. So you can have a function such as this sine 44 degrees. And if you want to solve it, you have to pick the appropriate value for a. And a is usually a value that's close to that, and it's a value that's known to us. So for instance, 44 degrees, that's very close to 45 degrees. Okay, a typical angle, especially when you talk about right-angled triangles, where you can have 2 triangles with 45-degree angles and the last 45 degrees and the last angle being 90. Okay, so you can pick a known angle, 45 degrees or 30 degrees or 60 degrees, and use that as a, and then solve for the Taylor series expansion before substituting in the new value. Okay, you can also use it to approximate stuff like square roots. Like, we know the square root of 9 is 3, but what about the square root of 9.1? Okay, we can use Taylor series approximations to look at those as well. Before we do that, though, I want to refresh you on radians and some of these angles that I talk about for sine and cosine functions, okay? So, starting with radians, okay? So, radians talk about revolutions, all right? And for one revolution around a circle, regardless of the diameter or the radius or anything, it's 2 pi radians. Okay? We also know that in a circle, there's 360 degrees. So using those two numbers, we can figure out that 1 radian is approximately 360 degrees divided by 2 pi, or 57.3 degrees. So almost 60 degrees. Okay? Using that same logic, 1 degree is actually pi divided by 180. Okay, so terms to know, again, terms I will provide you on your formula sheet, but that's just talking about radians, okay, because that's kind of the fundamental piece when we talk about trigonometric functions. For each of these items, when I use a Taylor series expansion, you have to use radians. Okay, so you can't put in 45 degrees. You have to put the radians equivalent, which in this case we'll talk about in a second, is pi by 4. Okay, you also have to make sure that your calculator is set to radians. So make sure the little mode at the top says R, or for some of you it might say RAD, and make sure it does not say D or DEG for degrees. Okay, because when you go to do your final answers for these questions, you will not have the correct setting. So on that note, I'm going to talk about basic functions, and I want to talk about trigonometric values as they relate to a right-angled triangle. Okay, so looking at a right-angled triangle, we have 3 sides. We'll call it X, Y, and R. R being the long side, which is known as the hypotenuse. You can also look at them as the side opposite the angle. So if the angle is theta, this would be the opposite side. This would be the adjacent side, and this would be the hypotenuse. So you can think of angles in terms of these. So sine theta is equal to the opposite side divided by the hypotenuse. Okay, keep in mind we're talking about lengths. Cosine is the adjacent side divided by the hypotenuse. And the tangent is the opposite side divided by the adjacent side. Okay, and what we do is if we have just functions like sine of x or cosine of x, we can use some famous triangles that have been calculated to figure out what the values are of specific angles. So what I'm talking about are 3 major angles: 45 degrees, 60 degrees, and 30 degrees. Now, if you convert those to radians, what they convert to using this formula here is pi by 4 for 45 degrees, pi by 3 for 60 degrees, and pi by 6 for 30 degrees. Okay? The other thing to note is if you start taking the sine, cosine, or tangent, again, you go back to using opposite over hypotenuse, or adjacent over hypotenuse, or opposite over adjacent, depending on which function you're talking about. But the values that are listed here are for specific triangles. And the 2 triangles that we often see, okay, the first one is where you have a right angled triangle and your angles are 45 degrees and 45 degrees. Okay? For simplicity, these sides follow the similar ratio. The 2 sides that are opposite the 45 degree angles have the same length, so we just write them as 1 and 1. Okay? It could be 2 and 2, 3 and 3, it doesn't matter. But for the sake of this, we talk about 1 and 1 as the base case. The hypotenuse can be calculated, remember, from Pythagorean theorem. So it would be 1 squared plus 1 squared is equal to the hypotenuse squared. So the hypotenuse, if you solve for this, is root 2. Okay? The next triangle is looking at the remaining two angles, 30 and 60 degrees. So it starts with a right angle triangle, and you have one angle is 30 degrees and one angle is 60 degrees. Okay? The reason it has to be in these ratios is the angles in a triangle have to add up to 180 degrees. In this case, we start with the smallest side, which would be the side opposite the 30 degrees. We call that 1. Okay? The hypotenuse we call 2, okay, so the full length, which means the final side must be 2 squared minus the other side, which is 1 squared, which is 3, and then the square root of it, remember using Pythagorean theorem. So this triangle is called the 1, 2, root 3 triangle, okay? So using those values, we can come up with the answers for sine, cosine, and tangent of these three angles, 30, 45, and 60 degrees. So starting with 45 degrees, which is pi by 4, the sine of pi by 4, remember, is the opposite divided by the hypotenuse. So the opposite side here on this triangle is 1, and the hypotenuse is root 2. So you're left with 1 divided by root 2. The cosine is the exact same. Okay, it's the adjacent side, which is 1, divided by the hypotenuse, which is root 2. So you have 1 divided by root 2. For tangent, it's the opposite side divided by the adjacent side, which is 1 divided by 1, which gives you 1. Okay? So I'm just explaining where these values are, again, come from. Again, I will provide you these for your test. The next is 60 degrees. Okay, so you see our 60-degree angle sitting here. And the sine of the angle is opposite divided by our hypotenuse. So the opposite side is root 3, hypotenuse is 2. So sine of that angle is root 3 divided by 2. I actually like to draw these triangles on tests that I used to write because it makes it easy for me to remember them as opposed to a table. The cosine of pi by 3 is the adjacent side, which is 1, divided by the hypotenuse, which is 2. So we end up with 1 over 2. Okay. The tangent is the opposite side, which is root 3, divided by the adjacent side, which is 1. So we end up with just root 3. Lastly, for 30 degrees, okay, we have the sine of pi by 6. Okay, so we're at 30 degrees. The opposite side is 1. The hypotenuse is 2. So we're left with 1 divided by 2. Cosine is the adjacent side, which is root 3, divided by the hypotenuse, which is 2. So we're left with root 3 divided by 2. The tangent of pi by 6 is equal to the opposite side divided by the adjacent side, which is 1 divided by root 3, which is how we obtain our answer there. Okay, so I'm just running you through these so you understand these angles. You're going to see they come up when I start trying to solve for a specific angle using sine or cosine and the Taylor series. Okay, so with our refresher course on trigonometry completed, let's look at our first example here. Calculate the approximate value of cosine 44 degrees by using the first three terms of the Taylor series expansion using the appropriate value for A. So just like we talked about, this is 44 degrees, and we know one of the well-known angles is 45 degrees, which we know is pi by 4. So knowing that, I'm going to select A to be pi by 4. Okay, remember, for all of these, it has to be in radians. So when I provide you with an angle in degrees, you have to convert it to radians. Okay, so we know that pi by 4 is 45 degrees. And you remember, okay, so we'll start by writing A is equal to 45 degrees, which is pi by 4. We know that 1 degree is equal to pi by 180. So we know that 44 degrees must be equal to pi by 4 minus 1 degree, which is minus pi by 180. So that will come into play later on. I'm just doing that kind of legwork now. So we're going to approach this with a value of a of pi by 4 the exact same way that we have approached all of our questions so far. So we start by writing out the Taylor series expansion. So we have f of x is equal to f at a plus f prime at a times x minus a. And we only have to do 3 terms this time. So with our third term, f double prime of a divided by 2 factorial x minus a squared. So we're only doing 3 terms here. And what you're going to see is how accurate the Taylor series is at approximating it with just 3 terms. Keep in mind that a lot of this math has useful applications, but when it was first created, a lot of it was to be able to find these answers, like 44 degrees, when we didn't just have a calculator you could buy in the bookstore for $9.99, or for some of you that have scientific calculator apps on your phone. Okay, that stuff wasn't available when this math was initially derived. So with that, I'm going to look at the functions now. Okay, so we know that f of x, we're going to just say it's cosine of x, right? Because we gave an angle here, but it's just an angle, right? It's not 2 times an angle, it's not 4 times an angle. So we know the function must be just cosine of x. So knowing that, f prime of x is simply negative sine of x, knowing the derivatives of cosine. And the second derivative, f double prime of x, is negative cosine of x. Okay? Simple, straightforward. Now we know that a is pi by 4. So solving for each one of these, we have the first function, f at a, which is f at, I wrote a, but we'll write pi by 4, is equal to cosine of pi by 4. Remember, okay, I always like to draw the triangle. So you can go back to our formula sheet and you can see the values that are in the previous slide, or you can just try and draw the triangle. So we have a 90 degrees, 45 degrees, and 45 degrees. Remember, these sides have to be the same because this is an isosceles triangle. So they're 1 and 1, which means the hypotenuse is root 2. So cosine is equal to the adjacent side over the hypotenuse, which is 1 divided by root 2. So the cosine of pi by 4 is 1 divided by root 2. F prime at the same number, pi by 4, is equal to the negative sine of pi by 4. Again, sine of pi by 4 is the same. It's the opposite side, which is also 1 divided by the hypotenuse, which is root 2. So we end up, again, instead it's negative 1 over root 2. The second derivative, f double prime at pi by 4, is equal to negative cosine of pi by 4, which we know is 1 over root 2. So this is just simply negative 1 over root 2. Okay, so you can see that you could plug those numbers in your calculator. But for example, 1 divided by the square root of 2 is going to give you 0.7071 more decimal places. So it's easier to write it in fraction form by knowing these triangles. By all means, you could plug that in your calculator. Forget I even talked about knowing these answers to these angles. I'm giving you both options, but these ones you'll notice make the math a little bit simpler. Okay? So now that we know those values, we can simply substitute them into our Taylor series. So we have f of x is equal to f at a, which is 1 over root 2, plus f prime at a, which is minus 1 over root 2 times x minus pi by 4, plus, in this case, f double prime, which isn't a plus, it's a negative because it's negative 1 over root 2, divided by 2 factorial, don't forget that, times x minus pi by 4 squared. So now we have the Taylor series. So the trick is knowing that we have 44 degrees, we can substitute 44 degrees in and find the answer. Okay, it's as simple as that. So remember what we calculated at the start was that 44 degrees was equal to 45 degrees minus 1, okay, which is pi by 4 minus 1 degree. Again, remember from our last slide, which was pi divided by 180. So we can substitute this value in to our Taylor series. If we do that, we get f at, in this case, x. X is pi by 4 minus pi by 180. Okay. It's equal to 1 over root 2 minus 1 over root 2 times x is pi by 4 minus the 1 degree, pi by 180, and then minus a, which is pi by 4. Okay, you're going to see that with the proper selection of a, we can cancel out those pi by 4s. Then our last term is minus. This becomes 1 over 2 root 2. Okay, that's just simplifying 1 over root 2 divided by 2 factorial, times x, which is pi by 4 minus that degree, pi by 180, and again minus pi by 4, which is the a value. That is all squared. So again, you see that the pi by 4s cancel. So what we're left with is that f at pi by 4 minus pi by 180, or 44 degrees, is 1 over root 2 plus, in this case, multiplying these two together, we have negative 1 over root 2 times negative pi over 180, which becomes pi divided by 180 root 2. And the last one becomes minus 1 over 2 root 2 times pi, or negative pi by 180 squared. Okay? You could have done that in your calculator as opposed to simplifying it here, because now you have to put these numbers in your calculator if you're going to get a final answer. So if you do, you actually get a final answer of 0.71934. Okay? If you were to just take that number and place it in your calculator, so if you were to do cosine of the pi by 4 minus pi by 180, you would have arrived at 0.7193398. So you can see that we're off by such a small margin, okay? It's actually 2 times 10 to the negative 7 that we're off. So this expansion with only 3 terms, again, it's supposed to go infinitely, comes up with a very, very accurate solution very quickly, okay? The terms would start to taper off to be so small that they no longer play a role in calculating that estimated solution. Okay, so you can kind of see how they work side by side. So now what I want to show you is I want to show you what the value would be for that same question, cosine of 44 degrees, if I use the first 3 non-zero terms of the Maclaurin series expansion, okay? And we're going to compare those values to see how close they are. They're not going to be the same because they're different series expansions, but we'll see how similar the answers are. So before I go into this question, there's a couple items that I want to write down, and they're from our previous question. So if you're following along, know that we picked a of pi by 4, which doesn't do anything from the Maclaurin series because it's when it's 0. But remember, 44 degrees was equal to pi by 4 minus pi by 180. The other thing is, if you do not have your formula sheet and you're trying to do this question, make sure you grab it, because the other thing is we know for cosine of x what the expansion is. So we're not going to derive it. Those expansions will be provided to you on the test. We know that if f of x equals cosine of x, the expansion is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and it keeps going. But those are the first three non-zero terms. You'll notice I wrote non-zero because the x to the 1 term and the x cubed terms are not here. Okay, that happens in the Maclaurin expansion because we use functions at 0. Okay, so this is already being solved for us. We simply now have to substitute in our value for x. In this case, pi by 4 minus pi by 180. So if we do that, we get 1 minus pi by 4 minus 1 or pi by 180 squared over 2 factorial, which is 2, plus pi by 4 minus pi by 180, the exponent 4, divided by 4 factorial, which is 24. If we add all of these up using your calculator, I recommend taking this kind of in steps, doing the squared terms first, then dividing by 2, just to make sure you get the order of operations correct. But if you do, you'll get 0.71962. Now, remember what our solutions were in the previous question. When we used the Taylor series, we got 0.71934. And when we used just our calculator and put in cosine of pi by 4 minus pi by 180, we got 0.719338. Okay, so you can see that we're still a little bit off, okay, in the 4th decimal place using the Maclaurin series versus pretty much being exactly the same on the Taylor series. Now this won't happen for all values, but you can see that as the value of x gets smaller, they'll get closer and closer. So there is a difference between them, and overall the Taylor series is the more accurate solution, okay, over a wider range of x terms. So I just wanted to show you the comparison between the two. Okay, so let's look at our last example. We're going to look at a root function. So calculate the approximate value of the square root of 15.85 by using the first 4 terms of the Taylor series expansion and the appropriate value for a. Again, keep in mind that we can use these expansions to solve for what were, complex functions before we came out with something, with our calculators, right? This allows us to approximate those functions by using math, okay? So basic, math principles and translating this root function into something that's more easy to calculate. A square root is you're trying to find two numbers that multiply together. If we can break it out into polynomials like we are doing, those are numbers that you can actively calculate without a calculator. So looking at this, just like our sine and cosine functions, we were always looking for that known value. Okay, so 45 degrees or 30 degrees or 60 degrees. And it's no different here. You want to find a value for a that is a known square root, right? So 15.85, I don't know the square root of. Okay, not off the top of my head. But I do know that the square root of 16 is equal to 4. So I know that a good value for a here would be 16 because it's a known square root value, right? It's a starting point for us. So I'm going to start with a of 16. And just like I did in the past, I'm going to start by writing the Taylor series out. So f at x is equal to f at a plus f prime at a times x minus a plus f double prime at a divided by 2 factorial times x minus a squared. And our 4th term, f triple prime at a divided by 3 factorial times x minus a cubed. And this would obviously continue on, but we're only looking at the first 4 terms. So when we look here, we know that it's the root of a number. So our function, f at x, is the square root of x, okay? Or x to the 1/2. Okay, I usually write it as an exponent because then when we take the derivatives, you can use the power rule. So f prime of x is equal to 1/2 times x, and subtracting 1 from the exponent, you get negative 1/2. The second derivative, f double prime of x, is equal to 1/2 times negative 1/2. X, in this case, subtracting 1 again to the negative 3/2, which simplifies to negative 1/4, x to the negative 3/2. And our third derivative, f triple prime of x, is equal to negative 1/4 times negative 3/2. X, again subtracting 1, we get negative 5/2. So simplifying this, f triple prime of x comes to 3/8 x to the negative 5/2. Okay, that's just me substituting in, or that's just me taking those derivatives. All right. So now if I substitute in 16, for our first function, we get f at a is equal to the square root of 16, which is 4. F prime at a, okay, we get 1/2 times, in this case it's 1 divided by the square root of 16, so this comes out to 1/8. F double prime at a, okay, is equal to negative 1/4 times 16 to the negative 3/2. I like to use my calculator when it's not the simple root, so let's say in this case it would be the root of 16 cubed. You could do it either way if you want to. Just remember that button, mine looks like a to the b/c button, you can convert it back to a fraction. I find that that helps. If you do that, you get negative 1/256. For our third derivative, f triple prime at a, we get 3/8 times 16 to the negative 5/2. Okay. If we put that again in our calculator and find a fraction, you'll see the fraction's getting increasingly large, right? And what that's saying, if you remember, is that these terms are going to be smaller and smaller and smaller and play less of a role in determining the overall final answer. We multiply this out, we get 3/8192. As you can see, very large numbers. So, knowing what these are, we can now substitute them into our equation. And what we end up with is that f at x, I'll draw a line here so that it's not too busy. F at x is equal to 4 plus 1/8 times x minus a minus 1/256, remember, divided by 2 factorial, x minus a, and I should have wrote that a is 16 here. So x minus 16 squared. And our last term, okay, which is plus 3/8192, x minus 16 cubed. And that's divided by, remember, 3 factorial. So now we have this, okay? We can substitute in our value now for x, which is 15.85. If we do that, we get f at x is equal to 4 plus 1/8 times 15.85 minus 16. Minus, if I simplify this, 256 divided by 2 gives us 1/512 times 15.85 minus 16 squared. And our last term becomes this massive number, okay? 1/16,384. Again, almost becoming obsolete in this calculation. And that's kind of what I'm trying to show you with the fourth term. That's multiplied by, sorry, not x, 15.85 minus 16 cubed. Now again, putting these numbers now in your calculator, see, I know I say, oh, put them in your calculator now, and you're probably wondering, you said they didn't have calculators then. But these types of polynomials, they can multiply together. Remember, you could do multiplication and division by hand before you had calculators, or you could use a slide rule. So if you do that, you get that f at x, in this case, is equal to 3.9812. If you put that in your calculator, the square root of 15.85, you get the same number, okay? 3.9812. You might get something slightly different for the later decimal places, all right? But you get an answer that's accurate to 4 decimal places, all right? So you can kind of see how using these expansions can derive very accurate solutions. So that was it for this lesson. We're just going to cover Taylor series. Our next lesson, we'll start looking at Fourier series, which are periodic functions. Okay, so periodic functions being similar to sine and cosine, just combining them together to make more complex waveforms. So I recommend looking at these practice problems, trying them out. Once you expand the series, Taylor series, a few times, you realize that the steps are the same. So as long as you can follow the basic derivatives that we've done, oftentimes using the power rule, we're not going to have crazy functions, where you have to use integration by parts, something like that. Okay, they're going to be relatively, they're going to be more, easier functions to differentiate. If you have any questions, send me a message on Teams or send me an email. Thanks, everybody.